Alright, so I'm going to teach you about critical points. Critical points are basically straight up where the derivative of a function is equal to 0. So, we'll denote from here on out, the derivative of a function will be written as f prime of x. And the second derivative of a function, which is the derivative of the derivative, will be written as f prime prime of x. So, critical points are useful in that they tell us where a function has a maximum or minimum value. Basically, where it has the top of a hill or the bottom of a valley. So, not all critical points are extrema, as we call them, maximums or minimums or extrema. Some are just inflection points, which we'll learn more about later on in the next video. Like in x cubed here, the derivative has a 0 here, but there's no change in, there's no maximum minimum. But we'll get onto that later. So let's start with an example. Let's try our function x squared plus 4x plus 4. Now, that's what we know, that it looks like that, but say we didn't know, and we wanted to try see what could we learn about this function based on what we know about its derivative. So we know its derivative, f prime of x, is 2x plus 4, and we know that this is equal to 0 at x equals negative 2. Therefore, we have a critical point at x equals negative 2. And, well, we know how to graph this line. It's just a straight line going up, passing through negative 2. Now, looking at our derivative, notice it's negative, 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 0, positive, 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 positive. So if we have a negative derivative, that means that our function is decreasing, which is reflected accurately in our rendering of our x squared plus 4x plus 4 function. So our function is decreasing, 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 decreasing. Where our derivative is equal to 0, we have a critical point, and then our derivative is positive, so that means our function is going to be increasing, increasing, increasing. So that's how we use our derivative to help us draw our function. So if the bottom of a valley, the bottom of a cup, is known as a minimum. Now, say we had a function f of x equals negative x squared minus 4x minus 4. Well, the derivative, f prime of x, would be negative 2x minus 4. And then our derivative is equal to 0 at x equals negative 2, which means we have a critical point at x equals negative 2. So we can draw a derivative, and it has a 0 at x equals negative 2, and here our derivative is positive. Even though our derivative is decreasing, it's still positive. So that means that our function is going to be increasing, like it is here, until it reaches its critical point, and then it's going to be decreasing, because our function here is negative. So here we've accurately rendered our graph based on what we know about its derivative. And where we have the top of a mountain, the top of a hill, the top of a hat, whatever, that's a maximum. So now let's look at a critical point that's neither max or min. Say we had the function x cubed. Well, our derivative of x cubed, f prime of x, is 3x squared, right? And our derivative is equal to 0 at x equals 0, because 0 squared times 3 is 0. So that means we have a critical point at x equals 0. So, okay, this is our derivative, f prime. So what should our function look like? We have a positive, so our function's increasing, 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 increasing. Wait, our derivative is still positive, so our function's still increasing. So there's no change from increasing to decreasing. So there can be no extrema. So not all critical points are extrema, but all extrema are critical points. So just keep that in mind.